So we're looking at, what are we looking at here?
We're looking at two cameras on a Servos, and it's the cat tracker.
Independent tilt pan.
Independent tilt pan. They should individually find the cat and individually track it.
And each camera feeds into this individual BT878 video capture card.
Yeah, each has its own capture card.
And you've written a driver that handles the two cards on two different interrupts? Same interrupt?
Two different interrupts.
Two different interrupts. Okay, great. And we're going to see it track the cat with stereo vision here, and you've also got some streaming debug, it sounds like, as well.
Yeah, and over on the VxWorks terminal, we've got the distance calculation that's going to be streaming over there, and that's based on the angles of both the cameras. It takes them both and calculates the distance to the cat.
Okay.
So, turning it on, and the cameras are going to flip up.
Okay.
And hopefully find the cat. They may find your foot or something. It depends.
I'll try to stay out of the way here for you.
It depends on what
Okay.
you see.
I see, and you can see distance coming out on the VxWorks terminal.
As long as the cameras aren't moving, the distance isn't changing, so you don't see additional messages. So now we are trying to connect debug.
Ah, nice. There's the streaming debug, and I'll zoom in a little bit on that. Okay, and you can see a nice edge of the cat. It almost looks like it's got whiskers moving, sorry.
So we can change the what
Getting
color.
a little cheesy here, but that did look like a cat face for a moment.
We can change what color channel it's looking at to detect.
Okay.
So what we just saw, it's looking at all colors, and it's averaging the red, green, and blue.
Okay.
What we saw a second ago was it was looking at just the red channel.
Okay.
And
yeah, that's where it looks like it has a face. So that's a pretty solid edge on the cat. Let's go look over at the cat. I mean, there's whiskers on it. You can basically see some amount of the whisker definition, even over here. And you've got the centroid of the cat.
Definitely. He's right in the center.
Yep.
You're actually seeing two centroids there, one on top of the other. One is we've got the center of the camera always marked in green, and then we've got the center of the object in blue.
Got it.
And so we're always trying to move the blue to the green.
Yeah.
So we'll move that in a minute.
And they get
so you can see the air between the center of the field of view and the centroid of the object it's tracking at all times. Okay.
And if it's close enough, I think, is it within a degree?
Within half a degree.
Within half a degree, then it doesn't move the cameras.
Okay. Right. So there's dead bands essentially, so it doesn't.
If you look at it, the picture kind of changes a little bit every capture.
Right. Yeah. There's some noise.
So that slightly messes up the angle, and so it will just keep going and going and going.
Okay, right.
So now we're looking at obviously the green channel.
Okay.
And then the blue channel on the screen.
Okay.
And the blue channel, you can see it's picking up a little more stuff that isn't the object.
Okay.
So the blue channel seems to have the most false positive object detection.
Okay,
so
interesting.
So we like green, actually.
Okay. So that's great. So you went through it and
red is what I meant to say.
Just experimented to find the one that works the best.
Yeah, so red works the best.
And this was added after our report.
Yeah.
This is new information.
Okay, great.
So you want to try moving the cat and see what happens?
Let's move the cat and see what happens.
All right. I'll try to keep my feet out of the way.
So as far as image processing, are you doing edge enhancement or things like that? No. Okay, just straightforward.
It just does a weighted sum of the indexes of all the dark pixels.
Okay.
And if you average the location of the pixels, it points to the center of the bar.
I see weighted sum above and below the line for X bar and Y bar, essentially. Is that right?
I don't know about the bar notation.
You're basically counting pixels that are inside the object.
Yes.
Above and below the X line and the Y line. And finding an equal number, or is it not quite like that?
It's just counting all the dark pixels in each row and in each column.
Okay.
And so
just row and column sums.
Yeah.
Okay. Yeah.
So it doesn't know about where the center of the camera is. It only knows about where the dark object is.
But basically, because of that approach, it doesn't have to be any sort of symmetrical object. It can be a blob.
It's any kind of blob.
And the number of pixels inside the blob above the line drawn across the x-axis would be roughly equivalent to the number below, and the same thing on the y. Is that not right? Yeah. Okay, so it's center of mass type calculation. Yes.
But of course, if you have 4 cats scattered around the room,
okay,
it'll average their location
between all of them.
Yeah. Okay. Makes sense.
Which means it's
would be the center of mass of the cat mass.
Yeah. So if
it's immune to some of the noise, little bits of pixels show up of darkness that's not actually the cat.
Okay.
And if you have a rather
still
fluffy
sees it.
cat, then, you know, it'll be weighted towards him.
Okay. So, okay, now explain to me the stereo vision aspect. So we've got 30 frames per second coming from each camera.
True.
And you've got, how do you fuse them together? I mean, they're not perfectly synchronized, right?
They are completely independent.
Yes, so asynchronous.
So there is no processing that involves both images.
Okay.
Each camera is its own stack of code.
Okay.
It's a copy for each one. They both have identical function.
Okay.
And so the output of that stack of code is merely how many degrees to the side of center the cat is.
Okay.
And then the controller of the servos receives that angular deflection and moves accordingly.
Okay.
And
so
at that
they're
point,
independently tracking the cat.
Independently track.
Yeah. Okay.
And so those angles that come in independently for each camera, that's what's used to calculate distance.
Okay. So so is there like a sensor fusion aspect though? In other words, that this can do better because it has two cameras independently tracking compared to say one camera independently tracking, I guess.
There is pluses and minuses. The minus is the downside is if we don't have one black object on one white background like we have stated to be the case.
Yeah.
They can start tracking different objects.
Sure. Okay. Makes sense.
And then the calculation for distance is silly, especially if they're both pointing away from each other. The cameras are kind of obtuse.
Mm-hmm. Okay.
Then obviously a distance calculation fails.
Okay.
So there is limitation that there's no interaction between the two. They don't know that they are both looking at these objects.
But you are doing stereo ranging.
Yes.
Given essentially the differences in the centroid that each camera sees and the baseline between the cameras.
Yeah, 12 inches between them.
Okay.
And whatever the angles are, and you can throw your trig at it and calculate the distance.
Okay. And so the distance, am I going to mess it up if I walk past here?
It will track you because you're black.
It'll recover?
Yeah, go ahead.
Well, it may not recover, it'll just track you.
Oh. I see.
You're the biggest
Now
black.
it likes you.
I see.
And
So I got to kind of get it to go back to the cat?
They'll follow you, yeah.
Okay. That's okay. I just wanted to get a picture of the screen here. So yeah, I see now it's actually tracking me.
Yeah.
But it is computing distance
We can just put our finger in front of it to make it go somewhere.
to try and get it. Okay.
It'll go.
So this
now it's
guy's tracking me and that guy's tracking the cat.
Well, he's actually tracking me right now.
Because he's a bigger black object.
Oh, okay.
Yeah,
In the frame.
And that was what we
I
were
see.
explaining where
So I can get them off of
have
you.
that problem.
Here, if you step out of the field of view.
If you can you command it back to the start position, for example?
Yeah.
We can,
Okay.
but when it comes back, it still has some angular deflection, and so it doesn't always come back to the cat.
Okay.
So we'll see though.
Okay.
Are you out of the field of view? I think probably. So
I think so.
This one is. Come here, you.
So left, right.
So he's found the cat, but this guy.
he's going a little crazy.
Yeah.
So
We didn't. This wasn't part of the intent. So yeah, we can freeze the motors, but we haven't added any logic to account for the
no problem.
What
the distance units? You have left, right, and I see units that are. You're starting over there again, or just stopping?
Well, I stop in one to recover this one, and secondly,
Okay.
you can see what the angles, what the distances were.
Okay. So yeah. So what are the units on that?
That's inches.
That's inches.
So he believes it's.
Distance left and right, 50 inches, average 49.5.
Yeah, I think it's somewhere around 50. The different numbers you see in there, you see a 15 and a 90. That's because this camera was just going all over the place. It was going in a circle.
His angle was changing quickly.
And the first two numbers are like some sort of raw values or something like
Yeah,
that?
actually,
Like,
Divide by 100,
it's, yeah,
okay.
and you get angles. 90, I think, is straight ahead.
yeah.
So the last one
I
here
see.
is 101 degrees.
Oh,
and
okay.
87 degrees.
Okay.
So 90 would be straight ahead, so they're off by 3 degrees, not from center.
And is that how you're commanding the servo? You're commanding it to that angle, or where are you getting that number from?
Pretty much, yeah. I take that angle, that's based on 180 degree deflection for the servo.
Okay.
And then I work that out to an absolute value between 0 and 3600.
Okay.
The actual command that you send to the servo.
Okay.
So it's basically a weighted proportion.
Okay.
And then these values here, the distance L and distance R, these are truncated values calculated. Okay. So this average is the only one that shows an accurate to a tenth of a digit.
Okay. And do you have a truth model to know that have you measured?
I've only measured by
if we get out of the frame, we
at
can
a specific distance.
Yeah.
And then
by knowing the distance in advance, measuring in advance, do you actually get within an inch of knowledge?
We're actually within 3 inches at about 10 feet because of the half a degree error in both cameras.
Sure.
So when you add up all the error, then
it sums up to about 3 inches of
how many angles per pixel are there?
Yeah.
What's the resolution of the...
Sure.
Right.
Okay. At 10 feet.
At 10 feet, yeah.
Okay.
So,
great.
Yeah, if we step out of the frame, hopefully it'll
Actually,
pick up the cat and calculate
We'll stay out of the way
the
then.
distance.
This time.
Okay. How far is the distance, you think?
So we're starting over. It found me again, didn't it? That's
well, while it's doing that, I'm going to go in there and measure and just see how far off we are.
okay.
So here we go. And this is showing me 58 inches.
Okay.
Yeah, so
And we had 50 inches.
it is 50 something or other.
Yeah.
We'll have to reset the thing and just see what it thinks it is.
Okay.
I'm going to get a clean start.
So let me get way away.
Let's see if that works.
Okay.
And there you go. And I saw a 54 in there.
Alright, so now if you look at the
51,
screen, you're seeing
51.3.
actual calculation of the cat.
Okay.
Yeah.
So at the end you see 50, 50, 48, 51.
Okay.
So
And you can get closer now since it's not looking
Okay.
over.
Right, as long as it doesn't get attracted
As
to
soon
me.
as it finds you.
Yeah, it just won't let go. I understand. Vision systems always seem to have that moth effect. You know, they find a bright light if they're going after something bright. In this case, the dark objects.
Yeah.
But it's not quite a moth effect. But okay, that's great. So 51 inches, we measured 58. And that's from the center of the baseline of the two cameras, or?
Yeah, at this point.
Right.
Right.
Okay.
Right, dead center between.
Right. Okay, that makes sense. And
If we were good, we could bring this closer
yeah,
and see the angle.
right. And we can see the distance going
It's about
down.
a foot, so
Yep.
It's about right.
Okay.
Because if the distance between the cameras is a foot, and that's about
Yep.
a foot, so it says...
So it's computing distance reasonably accurately in real time,
Yep.
tracking both cameras independently. All right.
And we put limiters on because another thing is I unwisely painted the base black.
Okay.
And so...
Oh, yes,
going
that's
to find
attracted to the base
itself.
sometimes.
Yeah.
Yeah, no, that makes sense.
We put limiters so
Yeah.
it will find itself now.
Right. Okay.
So now I understand why it would have been better to paint it white.
I guess you could have switched to a white cat on a black background.
It could have.
Just a joking. Pay no attention to me. I'm just the annoying narrator. Okay. Okay, so thank you very much. I think we got the idea here. Great project. And anything else you want to add for the audience here?
One more thing we
Yeah.
can do is we can take away this white and actually have a person walking around in the background with the room open, and it will track you reasonably well.
Right.
Um,
So if you're wearing a dark sweater like I am,
if
yeah,
I-
dark black shirt, yeah.
And so we've tracked all kinds of students walking through the room and
Yeah.
stuff, so works a little bit better than we had hoped for that. We did this whole white background just because that's what we had stated.
Sure, yeah.
We can actually just walk around in front of it.
It does
works too.
pretty well with a
It gets
cluttered
confused.
background.
It gets confused a little bit, of course, if it finds something bigger than a person. Or
So
darkness.
you could do some form of background elimination as well and try and
Yeah.
track just what's moving in the foreground. How hard would it be to adapt to, for example, to track like a face, like a flesh tone face?
Fairly hard.
Fairly hard, okay.
Because
You need high contrast.
Yeah.
Okay,
And if the cameras are moving, it makes background illumination all the more difficult.
okay.
You have to first do a frame alignment
Yeah, okay.
because your background is changing every time.
Oh,
the
sure.
camera moves.
Yeah, you'd have to do it.
And that takes some,
You'd have to do it periodically.
that takes some thinking.
Yes. Yep.
One of the things that we tried really hard to design this with the absolute minimum amount of CPU usage.
Okay.
And so we're doing very, very little processing. Our
Okay.
entire processing is in under 5 milliseconds.
Okay.
So we're definitely outpacing the frame rate. If we started to go to background elimination and frame
Yeah,
alignment,
more image processing.
we'd be chewing up a lot more of that.